Hello everybody. Let us try to discuss the statistical interpretation of quantum mechanics. Now, what does this actually mean? Actually, we want to look into this psi in detail, and this psi is known as the wave function. Right? We want to statistically look into what is the importance of this wave function in terms of statistics. Now, psi is a complex valued function. Psi, because it depends on the position x and time, so therefore this function, which is the wave function, this wave function is in one dimension, but we can extend the same concept uh, with three dimensions also. In that case, we will have to include y and z axis, y and z components also. In that case, the wave function will be a three-dimensional wave function. Now, at present, to simplify the discussion, we are discussing only wave function in one dimension, right? So then, as I just was trying to mention here, we can generalize it to include x, y, and z dimensions also. Now we can take the because this is a complex valued function, so we can take the complex conjugate of psi, and so if we take the complex conjugate and then we multiply the two functions, which functions, we start from this wave function psi, which is dependent on x and t. We take the complex conjugate of this function and the function itself, we multiply the two, and this will give me the magnitude squared of wave function, and this magnitude square is basically the probability density function of measuring certain outcome. Now, if when we are trying to do the measurements in the quantum system, we know that we cannot know the measurement outcome in certain terms, but we will be able to only know about the probability that this measurement outcome will come with this much probability. Now, from where this probability will come? Now, this wave function, square magnitude of this wave function will give us the probability associated with a particular measurement outcome. Now, as I was just trying to explain here, this magnitude square of wave function is basically the probability density function. This represents the probability distribution. Now, along x-axis is the position, is the for example, a particular outcome. Now, x-axis determines the position or any other quantity. That means in one case it can be position. Now, the position of the particle is defined by the x-axis, and y-axis will give me the probability density function, and this curve defines the probability distribution that what is the probability if the particle is at position A, or what is the probability if the particle is at position B. So therefore, it will give me only outcomes in terms of probabilities. Now, the area under, now let us say the particle can lie from A to B. It can be expressed as the area under the curve. That means the probability that x can be between A and B will be given by integration from A to B of this quantity, the square magnitude of the wave function. That means this gives me the probability of the particle being in position, being from position A to position B. That means the area under the curve. It will give me the probability. So therefore, to expand this concept further, the statistical interpretation of quantum mechanical wave function, often called Born interpretation, is one of the central ideas in modern quantum theory. Now, it connects the abstract mathematical form of the wave function to observable physical outcomes. That means it is trying to connect the mathematical wave function to the actual probabilities associated with the measurement outcome. Now, a quantum system is described by a wave function psi xt, which contains all the information about the state of the quantum system. Now, it is generally a complex valued function, so therefore psi xt can be the magnitude e to the power iota. So sxt is basically the phase. So it can be, the general equation of psi can be the magnitude term and the phase term with this exponential raised to the power iota sxt by h cross. Now the wave function itself is not directly measurable, rather we can measure probabilities derived from it. Now, according to Max Born in 1926, the square of the magnitude of the wave function gives the probability density of finding a particle at a given position and time. That means this is the probability of finding the particle at a position x at time t. This is given by the square magnitude of the wave function, and this I have just tried to explain this equation previously also, where you take the, because psi is a complex valued function, you can take the complex conjugate, the product of the two will give you the square magnitude. Now this means if you perform a large number of identical experiments, the fraction of the time the particle is found near position x is proportional to this wave function magnitude square. Now equation 1, what is equation 1? Let me just, so equation 1 is this, where to define the probability density function from point A to point B. Now equation 1 gives the probability of finding the particle at a position x between A and B. Now if we extend this A and B from minus infinity to infinity, so therefore x can be anywhere into the whole universe. So therefore this x extends from minus infinity to infinity, and in the limits of integration also it extends from minus infinity to infinity. So this is the area under the whole curve, because the particle must exist somewhere. This what does this equation tell us? This equation tells us that the particle must exist somewhere in space. If that is the case, if particle is there somewhere in this space, so therefore the probability of finding the particle is 1. So therefore this integration will output, the output of this integration will be equal to 1, because it is certain that at least the particle exists in the atmosphere, right? Where is the particle, that we may not know, but there is a possibility that the particle exists. Now this integration will solve to 1, right? Because the particle must exist somewhere in space, the total probability must be equal to 1. This condition is actually used to normalize the wave function. Now we can also find out the expectation value using the wave function. Now expectation value of an operator A will be given by the complex conjugate of a wave function into this operator A into the wave function. So that means psi star A psi will, and you take the integral. This is how we can find out the expectation value of a certain observable or an operator. Now for the case of position, let us say, so this will be equal to x into psi x square, because this psi conjugate and psi will give me mod psi x square, and x is the operator. In the same way I can find out the momentum also using the wave function. Now physical meaning of this magnitude square of the wave function is that it gives the probability of finding the particle between x and this dx. Now in the integral, if you see, you have x dx. So what is the meaning? The meaning is that it is the probability density, probability of finding the particle between x and x plus dx. Now if you are given a wave function, we need to normalize the wave function. This is very important actually. Now to normalize the wave function, you adjust it so that the total probability of finding the particle anywhere is 1. So that the total, so that normalization is important, so that a probabilistic viewpoint to the quantum mechanics, remains intact. And that can happen only if we normalize the wave function. That means the total probability must be equal to 1. So how to normalize the wave function? You start with the normalizing condition. So this is our normalization condition. Now if the wave function is not normalized, so definitely this integral will be equal to c, will be equal to some constant c, which is not 1. Had it been 1, so that means it is normalized, but it is not equal to 1, so therefore it is not normalized. Now, what we will do is we will introduce a normalization constant. So, normalization constant into psi x will be equal to the normalized wave function. Now, psi x is given to us, which is not normalized. We will multiply it with the normalization constant to get the final normalized wave function. So therefore you can find out the value of a from here, which would be 1 over under root of minus infinity to infinity wave function square dx. So this ensures the total probability to be equal to 1, because when you have normalized the wave function, this will ensure that the total probability of the wave function of finding the particle remains 1. This is how, this is the statistical interpretation of the wave function or quantum mechanics as a whole. Thank you.